going to tell you today what dark energy is. Dark energy is what black hole evaporation looks like from the inside. Our black hole universe is evaporating. I want to talk to you about perspective. Through time, the human perspective has changed. The trend is always towards recognizing we are in no special place. It begins with the individual. One person first realizing that other people are equivalent. This realization that the individual self is not the center of the universe, but that each other person around you has just a valid point of view of being the center. You then have to conclude that you as an individual occupy no special place. And now take our Earth. For a long time, people believed the Earth was the center of it all. The stars, the planets revolved around the Earth. And then we realized that wasn't true. The Earth was no special rock. It went around the sun. Eventually, we realized the sun was not even the center of our galaxy. It was in no special arm far from the center of our galaxy. Eventually, we realized that our galaxy was in no special place. It's not in the center of our universe. There are many other galaxies within our universe. And now we're coming to a time to recognize that our universe is no special universe. There are universes within our universe, and our universe itself is within another universe. What do I mean by this? Look around us in space. We now know there are black holes. We're learning more about these black holes, at least from looking at them from the outside. Each of these black holes, if you were inside of them, would look like our universe. From the outside of our universe, it looks like a black hole. In the next 50 years, we're going to learn a lot about what black holes look like from the outside as we observe the other black holes present in our universe. But for the next very long time, there's only one black hole we will know what it's like to be inside, and it is our black hole universe. So, I told you in the beginning, what is dark energy? Dark energy is our black hole universe evaporating. We know that the black holes we observe within our universe are evaporating. We know what that looks like from the outside. What does that black hole evaporation look like from the inside? Look around you. This is what it looks like from the inside. About 4 billion years ago, the expansion of our universe began to accelerate. I'm going to tell you about this transition. When I count to 3, you will wake up from this dream. 1, black holes have a temperature. 2, black holes are extremely cold. 3, thank you for staying with me. Now I'm going to continue the talk about dark energy. I'm going to show the math that helps us define the temperature of a black hole, and we're going to discuss how that temperature is related to black hole evaporation in its environment. So what is dark energy? Dark energy is a term that's used to explain a phenomenon. The phenomenon that we observe is that space and time is expanding all around us. People describe it as a tearing. Space and time are being torn apart, And dark energy is offered as the force that is tearing apart space and time. I'm going to tell you that dark energy is really just the phenomenon of black hole evaporation observed from inside the black hole that is evaporating. Black holes have a temperature. Fortunately, somebody else has figured out this equation. It looks very complicated, but it turns out almost all of these terms are constants. Constants that have already been discovered. The only term here that is not a constant is the temperature. This is T subscript H for Hawking. The Hawking temperature of the black hole and the mass of the black hole. So if you know the mass of the black hole, you can find the Hawking temperature. If you know the Hawking temperature, you can find the mass. Each of these constants here are on the sheet of paper. You can find them on the internet. This is called h bar. This is the reduced Planck constant. C is the speed of light in a vacuum. G is the gravitational constant. And Kb is the Boltzmann constant. So we'll plug each of these in for each of these values here. And as I said, just M and TH are left after that. I want to talk to you about a very important temperature in our black hole universe, on the inside of our black hole universe. It is 2.7 degrees Kelvin. This is extremely cold. Extremely cold. This is the temperature in the deepest of deep space, where there is nothing else. The vacuum. In the vacuum of our universe, it has a temperature. It is 2.7 degrees Kelvin. This temperature is radiating from every minuscule quantum of space-time. It's a very interesting phenomenon, and it defines our universe. So I rearranged this black hole temperature equation to solve for m. So I multiplied by m divided by th, and we get this. So what is the mass of a black hole that has that same temperature as our cosmic microwave background, 2.7 degrees Kelvin? Let's solve for that. If we plug 2.7 in here and use the other constant values that we knew, we find the mass of a black hole with a temperature equal to the cosmic microwave background of 2.7 degrees Kelvin as 4.5 times 10 to the 22nd kilograms. For reference, our moon is approximately this mass. So if you took a body approximately the size of our moon and compressed it into a black hole, it would have a temperature, it would radiate a temperature of 2.7 degrees Kelvin, basically exactly the same as our cosmic microwave background. So you can think of the cosmic microwave background as the temperature in the room. If something is hotter than the temperature in the room, it will evaporate. If something is colder than the temperature in the room, it will not evaporate. Here I've drawn an axis with the degrees in Kelvin on the bottom. This is indicating it's discontinuous. Room temperature for reference, 68 degrees Fahrenheit, is 293 degrees Kelvin. So we are way down in a very cold region here. So at 2.7 degrees Kelvin, if you have a mass, let me come back to this critical mass here. If you have a mass that is just, I'm putting it just smaller than 4.5. I'm putting it at 4 times 10 to the 22nd kilograms. Just smaller than that, it's going to be a little bit hotter. A black hole mass. I have to be very specific there. A black hole mass of a black hole with a mass of 4 times 10 to the 22nd kilograms will have a temperature of 3.1 degrees Kelvin. which is warmer than the cosmic microwave background, so it will be radiating photons as a black body, and it will evaporate. Its mass will slowly, very slowly decrease. Now, if you had a black hole with a mass slightly greater than this, let's say 5 times 10 to the 22nd kilograms, this would be colder, 2.5 degrees Kelvin. That would be colder than our cosmic microwave background, the room temperature in deep, deep space of 2.7 degrees Kelvin. Therefore, it's actually going to, a black hole of this size, mass, would actually absorb energy from the cosmic microwave background and continue to grow at a very, very slow rate. As we look at this, I want to explain or just mention one other phenomenon, that very slowly the temperature in our vacuum is declining. This is slowly getting colder. The other thing I want to point out, which may be counterintuitive, is that a heavier black hole is colder. A bigger, heavier black hole is colder than a smaller, lighter black hole. Smaller, lighter black holes are hotter. Now, this is where we're going to start to circle back to dark energy and the phenomenon of this observation. We need to think about what would black hole evaporation look like from 2 different perspectives. One perspective is from inside the event horizon. The second perspective is from outside the event horizon. From outside the event horizon, these are 3 different times, time 0, time 1, time 2. The observer is outside the event horizon. As time passes, if this black hole is evaporating, meaning its temperature is warmer than the cosmic microwave background in which it is residing, as time passes, for the observer outside the event horizon will shrink, and I'm showing radiation here, the evaporative radiation. This phenomenon of the shrinking black hole is what I described in lesson 1. The radius of this black hole for an outside observer is the Schwarzschild metric, 2gm divided by speed of light squared. As the black hole radiates energy and evaporates, its mass becomes smaller and its radius becomes smaller. So you can see it shrinks. That's the outside the horizon perspective. Now, the inside the horizon perspective is much more interesting. That's what we're experiencing right now. Inside the horizon, here we have, again, 3 different times. I'm putting you inside the event horizon. The event horizon is this slightly curved line out here. You're the observer. You're looking out into space at a distance, and you see 3 different objects, one at distance here, A, B, C. At this time, this is the arrangement of the objects. Now remember, we said space and time, according to the Hubble constant, are moving apart. The space is expanding. So for the observer inside the black hole, at the next time period, the space has expanded between the observer and A and B and C. And so we have the following. The observer now sees A as much further away, and B as now at the event horizon, whereas C was at the event horizon before. And now at the next time, A has now arrived at the event horizon. The event horizon, if you remember, is the distance at which space and time are expanding at the speed of light. So you cannot observe a photon from beyond that. This is the observation horizon. This observation horizon remains constant for an observer within the black hole. It appears, rather, that it's the space between all objects that is increasing. This perspective was what I described in Lesson 2, where the distance from the observer to the event horizon, is equal to the speed of light divided by the Hubble constant. That appears to be constant. But in reality, well, both of these are reality. From the outside perspective, this same phenomenon appears as this. Think about it. Please think about it. One more thing I wanted to share with you for perspective. We talked about the mass of a black hole with a temperature equal to the cosmic microwave background would be 4.5 times 10 to the 22nd kilograms. How big is a black hole with that mass and that temperature? So we can use the Schwarzschild radius metric to find that. And the answer is 0.07 millimeters. That is very small. And as I said before, if you took the mass of our moon, which is very nearly this, and made it a black hole, this is the size our moon would be if it was a black hole. Now, I hope you have a structure to think about dark energy from a different perspective, the inside perspective, and to recognize that it is so important to define the perspective of the observer, that things will look very different from opposite sides. And now you understand as well that dark energy is really just our black hole, which is a universe. Our black hole universe is surrounded by another universe, and that other universe has a cosmic microwave background temperature which is colder than the temperature our black hole universe appears within that universe. That means our black hole universe appears to be evaporating for an observer in the universe that surrounds our black hole universe. That's dark energy.